Hello and good morning, everyone. I guess everything fine, audible and visible. And if everything fine, please let me know. Or I would say, if there is any issue with audio or video, please let me know. So this is our last lecture. As you know, the name for the lecture series was Complete Syllabus on Group Theory. But I think you all will understand that it cannot be even possible to complete group theory in a week. Okay, but we have discussed some important topics from the group theory, and whenever it is possible we will come again with some more lecture series. Okay, and we'll discuss some more topics from group theory. Okay, this is our last lecture. Suprabhat, Akanksha, good evening. Manju, good evening, everyone. Okay, thank you so much. So in the last lecture, I think to complete group theory, at least we need 25 days. If you want to study group theory properly, then we need at least 20 days. Okay. So we will see if possible in the next week, or in the next week we will discuss some more topics from group theory. In the last lecture, we have started with normal subgroups. What is normal subgroup? We will recall the definition of normal subgroup and some more properties we discussed in the last lecture, and then we will discuss some more results. Okay, results and examples are also, and then we will talk about quotient groups as well. Okay, so let me start with recalling the things we did in the last lecture. Okay, what was the definition of a normal subgroup? Just give me 1 second. Good morning, Sunil. Good morning, everyone. Fine. So just a minute. Okay, so let me recall the definition of a normal subgroup. What was the definition of a normal subgroup? If let's say we have a group G and N is some subgroup of group G, we say that it is a normal subgroup if it has some property. What is that property? Is if every left quotient of N is same as the right quotient, you can say that N is normal in G. N is a normal subgroup of G if Nx is equals to Xn, right? For all X belongs to G, every left quotient of N in G is same as the right quotient, then we say that it is a normal subgroup. And to verify this, we have come to some simple way to verify whether a subgroup is normal or not, and that test was, you can say that N is a normal subgroup of G if you can say Nx inverse this belongs to N for all X belongs to G and for all N belongs to N. N belongs to N. Correct? If we can verify this, it means that we are saying this, right? So this was the simple way, and you can say that this was the test to verify whether a subgroup is normal or not, right? And we have seen some examples like AN is a normal subgroup of Sn for all N, correct? Center of G is always a normal subgroup of any group G, right? Center is always a normal subgroup. Then we have seen some more example. The trivial group 1 order subgroup is always a normal subgroup of any group G. Correct? G is always a normal subgroup of itself. G is always a normal subgroup of itself. Then we have seen, if let's say if H is a subgroup of group G and index of H in G is equals to 2, then H is a normal subgroup of group G. We have seen this, right? These are some examples and the results we have discussed in the last lecture. Let's move ahead. And now, just give me a second. Now, there are some more points. The very simple point is, you can observe, I think, by yourself also. If you consider, let's say, any group G, and it is a normal subgroup, sorry, it is a abelian group, then every subgroup of that group will be normal. If group G is abelian, left and right quotient, they will be same actually, right? There is no difference between left and right quotient. You don't even need to find the right quotient, right? Let's say G is, let me write this point and then we will verify. If G is a abelian group, if G is an abelian group, then every subgroup of G is normal. Then every subgroup of G is normal. Okay. Good morning, Nana. Radhe Radhe. Normal. Then every subgroup of G is normal. Okay. How we can see that? It's very easy to see that. If I consider, let's say, N is some subgroup of group G. N is subgroup of G. Okay. And G we have considered is abelian. G is abelian. So if you consider, let's say, define left quotient, how it is defined? xn, where n belongs to n. This is how it is defined. Correct or not, right? Since it is an abelian group, so we can write here x into n is same as n into x, where n belongs to n. Now it is nothing but the right coset nx. Every left coset is same as the right coset. Sapna, good morning. Good morning everyone once again. Fine. So every left coset is same as the right coset if group G is abelian for any subgroup H of group G or for any subgroup N of group G. So every subgroup of a group of an abelian group is normal. Let me ask you a simple question. Can you answer this? Find the number of normal subgroups of K4. Find the number of normal subgroups of K4. Can you find it? Find the number of normal subgroups of K4. How many normal subgroups does K4 have? Let me know your answer. K4, you know, I think I told you about K4. K4 is E, A, B and AB. It is a group of 4 order where one is one identity element and 3 elements of order 2. What do you think is the correct answer? How many normal subgroups K4 have? Akanksha 5. What about others? I think you all should answer this. It's a simple question. First, we should know that what are the subgroups of K4, and the second thing we should know is K4 is an abelian group. When it is abelian, okay, then every subgroup is a normal subgroup. So only we need to find is how many subgroups that K4 can have, right? Correct or not, right? So what are the subgroups of K4? What is order of K4? Order of K4 is 4. Correct or not? So if we consider any subgroup of K4, it should divide 4. Their order should divide 4, right? Order of any subgroup of K4, it will divide 4. So what are the possible orders for the subgroup of K4? It can be 1, 2 or 4. It can be 1, 2 or 4. Every time, whenever you consider any group G, it will have one subgroup of order 1, okay? That is trivial one, right? So one subgroup of order 1. And the number of subgroups of order 2 in any group G, I think I told you many times, the number of subgroups of order 2 in any group G is same as the number of elements of order 2. How many elements of order 2 are there? 3, right? 3 subgroups. What are those subgroups? Let me write all those subgroups. The trivial one is this. Let me write in this way. This one is the trivial one. Okay. Then we have subgroups of order 2. How many subgroups? Or 3 subgroups. So E comma A you can consider one identity element and one element of order 2. Then E comma B and then E comma AB. These are the 3 subgroups of K4 of order 2. Correct? Now, if you consider a group of order n, you want to look for the number of subgroups of order, that will be same itself for them. There is no other subgroup, right? So K4 itself is the subgroup of order 4 and which is 1, right? So K4 itself. So how many subgroups are there? Anju correct. Nana correct, right? 5 is the answer. I think you should answer it frequently, okay? So one subgroup of order 1, 2 subgroups of order 3 and one subgroup of order 4. How many subgroups? 3, 4 and 1, 5. Since group G is abelian, so every subgroup is a normal. They all are normal subgroups. Okay, you find coset of left coset and right coset of any subgroup, you will see that they are same. Correct or not, right? So K4 has 5 normal subgroups. I think it is clear. If there is any doubt, you can ask me. Now let's move ahead and we'll discuss some more properties. One result says that if let me explain this and then we will write it. If you consider a group G and H is some subgroup of group G and H has property that, let's say, order of H is equals to, let me say, n, okay, and H has only one subgroup of order n, which is H. There is no other subgroup G can have which has order n. Okay, so H is the unique subgroup of order n. Then H will be a normal subgroup. If H is a unique subgroup of their order, whatever order that H can have, okay, it is a unique subgroup of that order, then it is a normal subgroup. And it is also interesting to verify. Okay, let me first write it and then we will verify it. Okay, so what is this result says that if H is a unique subgroup of G of its order, unique subgroup of its order of, let me write in this way. Okay, so H is a unique subgroup of its order, unique subgroup of its order of G. What does it mean? If some order of H is n, then there is no other subgroup except H. There is no other subgroup of order n G can have with order n. So can you give a list of number of subgroups of important? Yes, China, I will give you. Okay, just wait for a few minutes and we will discuss that. Okay, so if H is a unique subgroup of its order of G, then it is normal. Then you can write then H is normal. Then H is normal subgroup of G, correct? And let's verify it. It will take only 1 minute to verify. We should know few points. The first point is, if H is a subgroup, then if you find XH X inverse, this is also subgroup XH X inverse. This is a subgroup of G. If H is a subgroup of G, then XH X inverse is a subgroup of G for all X belongs to G. You can verify this. XH X inverse is a subgroup of G. The second point we should observe is the order of this subgroup X, H, X inverse. This is same as the order of H. They both have same order. They both are subgroups of G. They both have same orders. Then since we say that H is the unique subgroup of its order, there is no other subgroup with the order same as H, right? So it means that it has to be same as H, implies that X, H, X inverse is equals to H for all X belongs to G, implies that you can say that X, H is equals to HX for all X belongs to G. We are done. We have proved that every left coset is same as the right coset of H, which implies that H is a normal subgroup. So in this way we can verify. So unique subgroup, whenever it is a unique subgroup, it is a normal subgroup. Let me ask you one more question and then we will discuss some normal subgroup of some important groups. Okay. So the question is, let me ask you, find the number of normal subgroups, find the number of normal subgroups of let me say Z10. Can you find the number of normal subgroups of Z10? Number of normal subgroups of Z10. Can you find this? Four, okay. And this is correct. See, it is an abelian group. You can use that fact also. Z10 is an abelian group. So every subgroup is a normal subgroup. How many subgroups Zn can have? Good morning, Himanshu. 4, Naina, Manju, Sapna, correct. 4 is the correct answer. Hai. See, you can use the fact that Z10 is a abelian group. So every subgroup is a normal and Zn can have tau n number of, total number of subgroups are tau n, right? So you can use that fact or you can use this information also. In a cyclic group of order 10, every subgroup is unique of its order, right? If you consider, let's say 10 has divisor 1, 2, 5 and 10. For each divisor, there is a unique subgroup, right? If you look at a subgroup of order 5, it will be unique inside Z10. Then it is also normal. You can use this result also or you can use this result to find this, right? So the number of normal subgroups, of Zn, subgroups of Z10 is equals to tau 10. How much is tau 10? Number of divisors, which are nothing but 4 divisors. So the answer is 4. Is that clear? Now let's see some list of normal subgroups of some important groups. Okay, normal subgroups of important groups. Subgroups of some important groups. Okay, some of them we have already discussed. Okay, like for example, let's say Zn. You know all the normal subgroups of Zn. Tau n, you can say it has tau n number of normal subgroups and every subgroup is a normal subgroup. You can even find what are those subgroups. If you consider, let's say D divides n, then group generated by n upon D, this is a normal subgroup of order D. It is a normal subgroup of order D. Normal subgroup of order D. Every subgroup is normal, so here nothing is special. Okay, fine. Next is K4. We have discussed about K4 also. Now itself, I think we have discussed. Let me write it. It has 5 normal subgroups. It has total 5 normal. So what are normal subgroup? Here also every subgroup is a normal because K4 is a abelian group. So this one order, two order, it will have 3 subgroups. We have discussed this. E, comma A, comma B, comma let's say E, comma AB, 3 subgroups of order 2 and one subgroup K4 itself of order 4. So these are the 5 subgroups that K4 can have. Now let's discuss about normal subgroups of Q8. We have discussed in the last lecture. What are the normal subgroups of Q8, right? Q8 is plus minus 1, plus minus I, plus minus J, plus minus K. So this is our Q8. What are the normal subgroups? If you remember, you can answer the number of normal subgroups of Q8. Let me know. Do you remember or not? Number of normal subgroups of Q8. How many normal subgroups Q8 can have? Total number of normal subgroups of Q8. Answer me and then we will see what are those normal subgroups. We have discussed in detail in the last lecture. Number of normal subgroups of Q8. Can you answer this? 6. Gina, okay. Let's see what are those 6. I think it is correct. Right? So, what are those normal subgroups? The first one is the trivial one. This is a normal subgroup. Okay. The second one is a subgroup center, right? Center of Q8. So, this is 1 comma minus 1, which is equals to center. Correct. Naina, Manju, Akanksha, Shabna, correct. Akanksha, okay. So this is our center of Q8. Center of Q8. This is also a normal center of Q8. Okay, this is normal. Then we have subgroups of order 4. Group generated by I, group generated by J, and group generated by K. You can write all those elements also. Plus minus 1, plus minus I. This is a normal subgroup. Plus minus 1, plus minus J. It is also a normal subgroup. They are indexed to subgroups, so they are normal. Plus minus 1, plus minus K, it is a normal subgroup. So how many there are? 1, 2, 3, 4, 5, and 1 is Q8 itself. So they are 6 in number. Number of normal subgroups of Q8 are 6. Now let's discuss the number of normal subgroups of group of symmetries. Okay, SN group. Normal subgroups of SN. So SN, you know, it is SN group of permutation on N symbol. So we will start with, let's say, S1. S1 will have one element, so it is isomorphic to Z1. It is isomorphic to Z1. Number of normal subgroups will be same as the number of normal subgroups in Z1, and it will have one normal subgroup, which is trivial one, right? So what is the order of S2? S2 is isomorphic to Z2. The order is 2, and any group of order 2 is isomorphic to Z2, and Z2 has 2 normal subgroups. What are those normal subgroups? That, you know, in Zn we have discussed, so I think it is not needed. Okay. So number of normal subgroups of S2 we know. Then what are the number of normal subgroups of S3? S3 has 3 normal subgroups. It has 3 normal subgroups, and those 3 normal subgroups are the trivial one, A3 group, the group of even permutations. We have discussed this, right? An in general, everywhere in Sn, any n, for any n, n is always a normal subgroup of Sn. And one more is S3 itself. There is no other normal subgroup. S3 has only these 3 normal subgroups. We will discuss some other day why they are the only normal subgroups. We need many things to state this, okay? How they are, right? You can verify these are the normal. It's very easy to see that this is a trivial one, so it is normal. This is improper one, so it is normal, and it is indexed to subgroup, so it is normal, right? We only need to verify that there is no other normal subgroup except these 3, right? With the help of class equation also you can verify that, but I'm not going to verify for 2 days. Okay. Okay. Fine. Now let's come to S4. What are the normal subgroups of S4? S4 has 4 normal subgroups. S4 has 4 normal subgroups, and the normal subgroups of S4 are identity, the trivial one, and S4 has one subgroup of type K4. Okay, normal subgroup of type K4, and one is A4, and another one is S4 itself. These are all the normal subgroups of S4. We only need to verify for this that this is a normal subgroup, and let me tell you the normal subgroup of S4 of type K4 is this: the identity 1 2 3 4 1 3 2 4 and then 1 4 2 3. This is the normal subgroup. You can verify that every left quotient will be same as the right quotient for this subgroup. Okay, So these are the normal subgroups of S4. Then we will have S5. I think some of you must be thinking that how we can verify that these are the normal subgroup. It will take some time. Okay, you can remember this, or it will take, I think, 2 to 3 lectures to explain this. Okay, we need to understand all the things about conjugacy classes, how we can look at a normal subgroup as the union of the conjugacy classes, what are the class equations of these subgroups, and many things we need. Okay, if you are interested, we will have some sessions and we will discuss that, but for the time being you can just remember what are the normal subgroups. Okay, so S5 has one this and another one is A5 and then S5. Not only S5, if you consider any other Sn where n is greater than or equals to 5, they will have only 3 normal subgroups, and these are the normal subgroups. If you consider Sn, it will have identity, okay, then An and Sn for all n greater than or equals to 5. Now we know the normal subgroups of every Sn. We know the normal subgroups of Sn. What are the normal subgroups? We know, see, S3 to except S4, if you accept S4 from S3 to Sn for all n greater than or equals to 3, you can say Sn has 3 normal subgroups. One is trivial, another one is improper, and one is An. Right? 3 normal subgroups. Every Sn except n equals to 4 when n is greater than or equals to 3. I think you can remember this. Okay, so these are the normal subgroups of Sn. Okay, now let's discuss the normal subgroups of Dn. Normal subgroups of Dn. I didn't taught you what are dihedral groups. I think you have some basic knowledge about dihedral group, then only we can discuss, otherwise we cannot. Okay, normal subgroups of dihedral group, let me say Dn. What are the normal subgroups of Dn? Let me tell you what is the structure of Dn is. Dn is looks like this. Dn is equals to E alpha square up to alpha to the power n minus 1, then beta alpha beta up to alpha to the power n minus 1 beta. This is how the dihedral group looks like. They are all rotations, and you can see that it is a cyclic subgroup of order n, they are all reflections of order 2. So this is our dihedral group. Now if we look at the normal subgroups of Dn, or let me say number of normal subgroups. I will tell what these type of normal subgroups, but first let's see the number of normal subgroups of Dn. What are those subgroups? We will discuss that. Okay, so number of normal subgroups of Dn is equals to every subgroup of only rotations is always a normal subgroup of Dn. You can verify that. Okay, if a subgroup of Dn contains only rotations, it is a normal subgroup. So how many subgroups are there? How many subgroups this subgroup can have? It is a cyclic subgroup of order n, so it will have tauian number of normal subgroups, and every subgroup will be a normal subgroup. Correct? Whether n is even, if let's say n is even, we will divide it in 2 cases. If n is odd, whether n is even or odd, we will always have tauian number of normal subgroups, the subgroups which has only rotations. Correct? So tauian number of subgroup, whether n is even or odd, we will have. Okay, which has only rotations. Then any subgroup, Dn itself is a normal subgroup, so you can sum here one, because Dn itself is a normal subgroup of Dn. Correct or not? Right? Now if n is even, we will have index 2 subgroups also. Okay, and how many index 2 subgroups will be there? They will be 2. Right? Index 2 subgroups will be 2. What are those subgroups? Dn by 2 type. Whenever you look for the subgroup of Dn, it is of dk type, or you can consider Dn by d type. D is a divisor of n. So any subgroup of Dn, either it is a cyclic subgroup or it is of the type Dn by d types, where d is a divisor of n. Okay, or you can say, let me say Dn by k type, because every time I am saying d, so it may not be clear to you. Okay, so any subgroup of Dn, either it is a cyclic subgroup or it is of the type Dn by k type. And when you look at the number of subgroups of Dn of the type Dn by k, they are nothing but the numbers in k. Okay, so they are in exactly k subgroup. Dn by k subgroups are k subgroups. So when you look for the dn by 2 subgroups, right, index 2 subgroups, one index 2 subgroup is already there inside tau n, only rotations, right, which contains only rotations. And these are the subgroups which has no half rotations and half reflections. So they are type of dn by 2, dn by 2 subgroups. Okay. So if n is even, then the number becomes tau n plus 3. If n is even, the total number of normal subgroups of dn is equals to tau n plus 3. If n is even, then it is tau n plus 1. We will not have these type of normal subgroups, because if n is odd, then we cannot consider this dn by 2. 2 will not divide n, so we cannot consider those type of subgroups. So this 2 will not be here, otherwise it is same. Tau n plus 3 if n is even, and tau n plus 1 if n is odd. So these are the number of normal subgroups. I think you understand what are those subgroups also, right? Here we know the subgroups with all the rotations, right? And if you consider any divisor of D, there will be a unique subgroup of order D inside tau n, right? And this one comes for dn, this one comes for dn, this 2 comes for dn by 2 type of subgroups. Okay, so the number of normal subgroups of dn is equals to tau n plus 3 if n is even, and the number of normal subgroups of dn is equals to tau n plus 1 if n is odd. Let me ask you a question. Find the number of normal subgroups. Find the number of normal subgroups of let's say D17. Let me say, find the number of normal subgroups of D17. Can you find this? If you don't know about dihedral groups even, you can answer this question, because we have this formula. So you just put the value of n and you can find it. Number of normal subgroups of D17. Number of normal subgroup of D17 is equals to tau 17 plus 1. So now you think 7, okay, 6, okay. What about others? D17 plus 1. D17 plus 1. So what is the answer? Number of normal subgroups of D17. Answer is 3, Akansha, right? I think Shonu, you should be careful. It is nothing but tau 17 plus 1. How many divisors 17 can have? It is 3, sorry, 2. 1 and 17, it is a prime number, correct or not, right? Sapna 3 correct, Cheena Manju correct. So this is 2 plus 1, so it is equals to 3. You can see what are those subgroups, right? Then correct. 3 is the correct answer. So it can have 3 normal subgroups. Number of normal subgroups of D17 is equals to 3. If I ask you, find the number of normal subgroups of D18, can you find it? Number of normal subgroups of D18. Number of normal subgroups of D18. So do you think 2, okay? What about others? Why it is 2? You're just answering randomly. Number of normal subgroups of D18. This is equals to, since it is even, so this is tau 18 plus 1 plus 2. And you should know that what are these subgroups actually. Okay, 9, okay. Rajesh, Akanksha, correct. This is correct. Manju, Cheena, correct. So what is tau 18? Tau 18 is 2 into 3 square, correct? 2 to the power 1 into 3 square plus 3. So it is equals to tau, this is equals to 1 plus 1 into 2 plus 1. 1 plus 1 into 2 plus 1 plus 3. So this is 3 to the 6 plus 3 is 9. 6 plus 3 is 9. D18 has 9 subgroups, and you should know what are these 9 subgroups actually. I think you can find all these 9 subgroups. What are those 9 subgroups? So this is tau 18. How this D18 will look like? Let me write it. E alpha square up to alpha to the power 17, then beta comma alpha beta up to alpha to the power 17 beta. So today's topic is not about dihedral groups, otherwise we can take some more time. So when you say the number of normal subgroups of D18 are tau 18 plus 2 plus 1, this 1 comes for D18 itself, right? This tau 18 comes for these subgroups of rotations, subgroups which contains only rotations, with only rotations, and you can find what are those subgroups. It is a subgroup of order 18, so 18 has divisors 1, 2 and 3, 9, and I think 18 how many 6 divisors, na? Right? 2 into 3 square, so this is 3 to the 6 also, 1, 2, 3, 6, 9 and 18. These are the 6 divisors. So tau 18 has one subgroup of order 1, one subgroup of order 2, one subgroup of order 3, one subgroup of order 6, one subgroup of order 9 and one subgroup of order 18. These are the 6 subgroups will come here, right? And this 2 comes for the 18 by 2 type of subgroups. 18 by 2 means D9 type of subgroups. It will have 2 subgroups of D9 type. D9 type means it will have 9 rotations and 9 reflections. We will consider half of the rotations and half of reflections. Half of rotations are fixed, while half of the reflections are actually will change it 2 times. That's why we are getting 2. Okay, we will discuss some other day. Okay, so these are the normal subgroups of dihedral group. I think these are some important groups that we should know the normal subgroups of. Okay, is that clear? Is there any other group you want the normal subgroups of that group? You can comment me. Okay, now we will move to quotient groups. How we can define quotient group? Let's say, just give me a second. Okay, so okay, fine. So now we will define what are quotient groups and how we can define quotient group. Let's say we have a group G. If we have a group G and we have a normal subgroup, let's say we have a group G and N is the normal subgroup of group G. Okay. Then what we do is we will collect all the cosets, right? We can construct cosets of any group G, any subgroup H of G, even it is not a normal subgroup, right? But we are considering here normal subgroup. We will get to know why we are considering this normal subgroup. So what we do is we will collect all the cosets of N in G, this type of cosets, right? AN, where A belongs to G. And why I'm writing left coset? Because here, since we are considering it as a normal subgroup, left cosets are same as right cosets. Okay. So we write only left coset. You can also write it as right coset also, right? We have considered only left cosets, right? So this collection also forms a group. Every coset here act like an element. Okay, I will tell you the operation with which operation this set forms a group. Okay, and this group is denoted by G by N. We call it as a quotient group. The collection of all the quotients forms a group with respect to operation. The operation is defined as AN star Bn. Now every coset behaves like an element. AN star Bn is nothing but A star Vn. A star V. And what is a star? A star is the operation of group. G is a group with the operation star. Then we define the operation AN star Bn is equals to A star Bn. Okay, this is how the operation is defined. We know what is A star B because this star A and B are coming from G, and A star is the operation of group G. So with this operation, this G by N is also a group. Okay, and this group is called the quotient group. What happens is we are actually dividing the group into some smaller parts, right? Let's say this is our group G, and let's say this is our normal subgroup N. So what happens is the same size, this group G is divided into some parts of the equal size. Let's say this is AN, this is BN, this is CN, this is DN, and let's say this is EN. Now we are studying this group. Every coset or every subset is act like as an element of the group G by N here. Okay, This is the idea. We are dividing the group into the smaller group and then we are studying that group. This is all about the quotient group. Okay. So this operation, why we are considering normal subgroup, let me explain this. This operation is well defined only for the normal subgroup. If you do not consider normal subgroup, this operation will not be well defined. What does it mean by well defined operation? When we say that an operation, let's say star is well defined. Operation is star, for the timing you forget about G by N group. Let's say we have group G. We have group G and we have operation star. When you say that this star is well defined, star is well defined means the phi function from G cross G to G is well defined. How this defined is, let's say phi of A comma B is equals to A star B. Okay. If this phi is well defined means this star is well defined. And when you say this phi is well defined, the function is well defined. We say that a function is well defined if A is equals to B. If two elements are same, their image cannot be different. One element cannot have two images, right? So if A is equals to B, f of A should be equals to f of B. This is the idea. Okay. So when you say that this phi or the star is well defined, because phi is same as star, right? You say that the star is well defined or phi is well defined, it means that if you consider A1 comma B1, because the elements here are this type of, right? They are ordered pairs. Let's say A1 comma B1 is equals to A2 comma B2, then phi of A1 comma B1, this should be same as phi of A2 comma B2. If this is so, then we say that it is well defined. Okay. And if it is not true, then we cannot say that it is well defined. So this is what we get here. You can say that if you consider operation on G by N group, it means that this is a function from G by N cross G by N to G by N group. And we say that it is well defined. It means that how it is defined, phi of An comma Bn, this will map to An star Bn and it is defined as A star Bn. So when we say that it is well defined, so phi is well defined, if let's say A1n comma B1n is equals to A2n comma B2n, implies that phi of A1n comma B1n, this should be same as phi of A2n comma B2n. If we get this, then we can say that this is well defined. What does it mean? Implies that when you say that An, it means that A1n star V1n, this should be same as A2n star B2n, correct? Or implies that you can say that A1 star A2 n is equals to A2 star B2n. A2 star, just a minute, correct or not, right? A2 star, you have B2 n. So if let's say what we are considering here, An is equals to An comma B1, A1n comma B1n equals to A2n comma B2n, implies that you can say that A1n is equals to A2n and B1n is equals to B2n. So what we need to verify that if A1n is equals to A2n and B1n is equals to B2n, then we need to verify that A1 star A2n is same as, this is not B1, A1 star B1, sorry, A1 star B1n is same as A2 star B2n. If we can verify that, then you can say that the operation is well defined. And if we consider n as a normal subgroup, we can verify that if this is true, then this is also true. This is what it means by well defined operation. If it is a normal subgroup, you can prove that. And if it is not a normal subgroup, it will not be true. Let me give you an example. So you consider, let's say S3 group. S3 has 1, 1, 2, 2, 3, 1, 2, 3 and 1, 3, 2. 1, 3, 2. I think 1, 2, 3, 4, 5 is next element. One more element is, let's say 1, 3. 1, 3, then 1, 2, 3 and 1, 3, 2. This is our S3 group, right? Let me consider a subgroup, ordinary subgroup. It is not a normal subgroup. Let me consider 1, 1, 2. 1, 1, 2. It is a ordinary subgroup. We will consider this one first. A1n equals to, let's say, A2n. So we consider, let's say, 1h is same as, you can say h or simply you can say 1h or simply h is same as 1 2h. 1h is same as 1 2h. You can see that because both are element belonging to h, so this will be equals to h. 1h is same as 1 2h. And if I found, let's say, to 1 3h. If I find 1 3h, what is 1 3h? 1 3h is equals to 1 3. I will do some I will skip some steps. Okay, so this is 1 3 and 1 3 into 1 2, 1 3 into 1 2. So this is equals to how much? 1 3 comma 1 3 and 1 3 beat 1 2. This is 1 2. Okay, 1 3 into 1 2 is how much? Can you multiply this? So let me write 1. 1 goes to 2. Now 2 goes to 1, 1 goes to 3. So this is 1 2 3. So if you see that this 1 3h, 1 3h is equals to 1 3h is equals to 1 2 3h, 1 2 3h. Why this is? I told you some properties of the cosets, right? What are some properties? Either they are identical or disjoint. Since 1 2 3h is common inside this, so 1 2 3 1 3h, this quotient will be same as this quotient. Correct or not? Right? Because 1 2 3 is inside this quotient. Is that okay? So they are same. Now we have this equation and this. Look at these two. 1h is equals to 1 3h and let me remove this 1 2h, right? And 1 3h is the same as. अगर मैं इन दोनों का if we multiply, if we do the operation of these two elements, this should be same as the operation of these two elements. Correct or not? This what it is, right? A1n is equals to A2n, then A1 B and V1 equals to V1n equals to V2n, then we should get A1 star V1n is equals to B2 star B2n. We should get this. Can you get this? Let's do this. If you multiply 1h operation 1 3h, this should be same as 1 2h operation 1 2 3h. Is it same or not? Can you find this? If you multiply those two, what we get is 1 into 1 2, which is nothing but 1 3, because this is identity element. H is equals to 1 2 into 1 2 3h. Can you see that? Are they same or not? Right? So this is equals to how much? 1. Let me write. 1 goes to 2, 2 goes to 1, so 1 will be fixed. Let me write 2, 2 goes to 3 and 3 goes to 1, 1 goes to 2 3h. Can you see that? Is 1 3h is equals to 2 3h? No, this is not correct. 1 3h is not equals to 2 3h. They are different two cosets, right? So they are not same. That's why the operation is not well defined. They have to be same. If this is equals to this equals to this, and this equals to this, so the operation of these two should be same as the operation of these two, if the operation is well defined. But since H was not a normal subgroup, that's why we are getting some counter examples. Okay, it is not same. To define this operation, we must have n to be a normal subgroup. If n is not a normal subgroup, this operation will not be a well defined operation. And if it is a normal subgroup, it will be a well defined operation, and you can easily verify that G by n is a group. Now let's see that G by n is a group. G by n, we say that this is a group with operation an star bn is equals to a star bn. Can you verify that this is a group? Let's look at each property one by one. So first property is closure property. If we consider these two cosets, it means that a is coming from n, b is coming from g, not n. A and b, they are coming from g. A star will also be inside g. When it is an element of g, it means that this is a coset by some element of g, so it is an element of g by n. Correct or not? The closure property is satisfied. Next is associative property. Associative property is satisfied by star operation in G, so it will here also. If you consider, let's say an star bn star cn, or you consider this is same as, you can write this is same as a n, and what is the operation of these two? This is equals to b star c n. Let me write in this way. B star C n. Correct or not? Right? Now what is the operation of these two? This is nothing but A star B star C and then n. Correct or not? Right? Since G has associative property, A, B, C, they are coming from G, so this is same as A star B n, B star C and then n. This is same as A star B. You can write A star B n and star C n. Right? You can break further. An star bn and then star cn, right? So easily you can verify. I think you should try all those things. It will be good for you to verify. Okay, so it has associative property because G has associative property with operation star. That's why it has associative property. Then let's look at the next property, existence of identity element. What is identity element? Can somebody tell me what is identity element of G by n group? You consider en. E is the identity of G. E is the identity of G. identity of G. E is the identity of G. So this En is equals to n. Why? Because E belongs to n. N is a subgroup, so n must have identity element. En is equals to n, and this is our identity element. This is identity of G by n. This is identity of G by n. You can see that easily. If you consider any element an from G by n, you do the operation A star with En, you will get A star E, A star En, and A star is what? Because E is the identity of group G. So this is again equals to An. Or from the left side, En star An also, this will be equals to n. This will be equals to An. So we are getting our original element An if we multiply or do the operation with En. This is true for all the elements. So En or n is the identity element of group G by n. Correct, Sheena, right? Okay. So next property is existence after existence of identity. What are some other properties we need to verify to be a group? Existence of inverse. So if I consider, let's say An, can somebody tell me what is the inverse of this element An? What can be the inverse of this element An? The natural guess, you take the inverse of A. So inverse of this An, inverse of An is nothing but A inverse n. The natural guess is this, and this will work. Okay, if you do the operation An, let's say An star A inverse n, this is nothing but A star A inverse n. Is that right? Since A is the inverse of A inverse is the inverse of A in G, so this will give you En, and we are getting our identity element of G by n. Is that or not, right? So An star A inverse n is equals to A star A inverse n, which is our identity element. It means that A inverse n is the inverse of An in group G by n. Correct or not, right? And this will be an element, that is also correct. A inverse n is an element of G by n, because A inverse is an element of G, since A inverse is an element of G. So A inverse n will also be element of G by n. It means that every element An has inverse in G by n. That's why it satisfies all the properties to be a group, and so G by n is a group. Okay, now let's look at some examples. Let's look at some examples. If I consider Z, set of integers, group of integers, okay, let me, since Z is a abelian group with respect to operation addition, so what we do is we will consider any subgroup, it will be a normal subgroup, right? So let me consider 6Z. 6Z is a normal subgroup of Z. So we can construct Z by 6Z group. What are the elements inside this? All the cosets of 6Z in Z. What are those cosets? You can consider 0 plus 6Z, 1 plus 6Z, 2 plus 6Z. Why we are writing plus here? Because in general we denoted the coset by An. So we should denote 0 into 6, 0, 6Z. But in this way, what we are not denoting, because when you say An, it means that you can write the operation of G here. The operation is addition, so we are denoting in this way. There is nothing special, okay? So I think you can understand this. So 0 plus 6Z, 1 plus 6Z. You can also denote this quotient An as A star n. In this way also you can denote this quotient. That's what we are doing.